Welcome back. In the last video, we defined a linear combination of a group of vectors. We also defined the span of a collection of vectors in Rn. All right, so let's do an example with it. Let's say I give you three vectors, v1, which is 1, minus 2, 3, v2, which is 4, 2, and 2, and v3, which is minus 5, minus 4, minus 1. I want to write this new vector, 3, 2, 1, as a linear combination of these three vectors. All right, so let's write what we need. So we want to find real numbers a1, a2, a3, so that w is equal to a1 v1 plus a2 v2 plus a3 v3. All right, so w is 3, 2, 1. A1 times 1 minus 2, 3. Plus a2 times 4, 2, 2, plus a3 minus 5, minus 4, minus 1. All right, so as long as you can find values a1, a2, and 3 that work in this equation, you have that w is a linear combination, and you've written w as a linear combination as well. But in this case, we're told that it probably works. We just need to figure out what a1, a2, a3 are that make it work. So let me join the three vectors. So I would get minus 2a1 plus 2a2 minus 4a3 as my second component, and 3a1 plus 2a2 minus a3 as the third. And so we want to make that equal to 3, 2, 1. So we end up with a linear system. A1 plus 4a2 minus 5a3 equals 3, minus 2a1 plus 2a2 minus 4a3 equals 2, and 3a1 plus 2a2, excuse me, minus a3 equals 1. I'm going to put that in a matrix. I'm going to reduce. Let me reduce for you. I don't want to spend too much time reducing. So I got 1, 0, 0, and then minus a fifth. Then 0, 1, 0, 4 fifths, and 0, 0, 1, 0. And so I get that a1 is minus a fifth, a2 is 4 fifths, and a3 is 0. And so my w, which is 3, 2, 1, is equal to minus 1 fifth, 1 minus 2, 3, plus 4 fifths, 4, 2, 2, plus, let me add the 0. I like having it in because we're asked to write it as a linear combination of three vectors. And even though we don't actually need the third, and we're not using it really, if I have the 0 there, it really shows that I've written it as a linear combination of all three. All right, so this specific W can be written as a linear combination of V, V2, and V3. In fact, if you look at the matrix we use, V3 is right here, V2 is this vector here, 4, 2, 2, and V1 is this one. So if you do it in Rn, it's pretty simple. You put your generators, the collection of vectors that you're given, as the first three columns, and then the one you want to build ends up being the constants. All right, so let's see how that works in the third case. I want to find conditions on x, y, z that ensures that x, y, z is in the span. And so really we're asking when x, y, z can be written as a linear combination of the three vectors. So we want this to be consistent. So we're going to set up the system just the linear system just the same. I'm going to remind you that this is what we have, right? We have those three building blocks, and then we're going to change the constants to x, y, and z, and that's going to be the new system that we want to be consistent, right? So let me skip to that right here. So 1 minus 2, 3, 4, 2, 2, minus 5, minus 4, minus 1. And then my new vector that I'm trying to build, that yellow vector, is now x, y, z. All right, so you want to know when this is consistent. Let me do it. I mean, it's not too long. So I'm going to use that 1 to get rid of the minus 2 and the 3. And so I will get row 2 plus 2, row 1, and row 3 minus 3, row 1 into row 3. I'm going to get, well, the first one doesn't change. Second becomes 0, 10, and minus 4, minus 10, minus 14, y plus 2x. And then 0, 2 minus 12 is minus 10. Minus 1 plus 15 is 14, and z minus 3x, right? So not so bad because I get something very similar. So the last thing I need to do, remember when you want to know whether a system is consistent, when you want to know how many solutions there is, you don't have to go to RREF. RREF is enough. So I'm going to leave the first row as is. I'm just going to get rid of that minus 10 and make that a 0. So I'm going to add row 2 to row 3. So row 3 plus row 2 into row 3. Let me do it on a separate line. Hopefully I have enough room. That's going to give me 1, 4 minus 5x, 0, 10 minus 14, y plus 2x, and then 0, 0, 0. And then I'm adding the 2, so I'm going to get z plus y, and then x, I get minus 3x plus 2x minus x. All right, so I have my two leading entries, so these rows are fine. The only question is whether that third row is consistent and not. It's going to be consistent when the last entry, so z plus y minus x, is 0. All right, z plus y minus x is 0, and so that's the span. So the span of v1, v2, v3 is the set of all x, y, z in R3 so that z plus y minus x is 0. All right, so I'm asked to describe the span geometrically. Well, we know that this means that it's a plane in R3. Because I have 0, it's going to contain the origin. 0, 0, 0, so it's easy to find a point. And I have, well, we could say perpendicular to the normal vector, or we could say parallel to the vectors we started with. So let's say that parallel to v1, v2, v3. So I have my plane, I have 0, 0, 0, and I have the three vectors I started with. All right, show that the span is a subspace of Rn. Now, whenever we ask you to prove that something's a subspace, we have different ways of doing it, right? We could prove the three conditions. We could prove the 10 axioms. At this point, we've proven that we can that any solution to a homogeneous linear system would be a subspace, and so that's what we have right here. All right, so W is the solution set of the homogeneous linear system. Z plus y minus x is 0, and so it is a subspace. We've proven that theorem. I think it was theorem 1.2.2. All right, that's it for now. Next video, I'm going to look at example 1.3.2. We'll do one where we actually have a description with equation instead of starting with a span.